Good morning, students. Welcome to the last lecture for this term. You'll probably have formal lectures only in the next 2 weeks. Or after the next 2 weeks. So 20th, I'll probably see you again. And of course, please take the time to make sure you get good marks for the first test at least. The second test, like I said, which the dates will be obviously communicated to you. It will be just want to see something. If my video is being shared here. It will be at the end of October. So I'm just making aware of that. Is there any questions before we begin? There's this book. Hello? You guys still there? No questions? Yes, okay. Okay. Yeah, guys, come on, man. We need some energy. We just got to push this. It's not too bad. All right, so I'm not going to recap too much because I really spent the time explaining that. What is going on here? Okay. So, you guys can see that's full slide. So we just talked about the concept of regeneration, and what it simply is, you're taking so I'll read it here. Regeneration increases the thermal efficiency of a Brayton cycle by capturing some of the waste heat from the exhaust gases and preheating the air before it is combustion. Obviously, if you think about this, you obviously require less fuel because you're adding more energy. So you have to burn more fuel for a specific amount of heat generated. A nice statement that is from your textbook. It says the thermal efficiency of the Brayton cycle increases as a result of regeneration. Certain proportion of the energy of the exhaust gases that is normally ejected to surroundings is now used to preheat the air into the combustion chamber. This in turn decreases the heat input. Thus fuel requires the same amount of net work output. Okay, so that's all what it essentially is. I normally ask theory questions like this. What's the purpose of regeneration? But I want to make you aware that that's all what it's about, right? Furthermore, I did mention there's a lot of other configurations, and fortunately for you, we'll already be doing the regeneration, right? This semester, I wanna kind of extend the refrigeration component of that section, because I normally I do the very basic one, which is fine, but I want to see if I can play around more here. I don't want to extend this too far. Okay, next. Yeah, okay, so I discussed this. Then two important things to note over here. And we basically got two new equations. It comes with the formula sheet, which is the effectiveness of the heat exchanger. I could have unpacked that further, but I don't want to waste time because we're not covering heat exchangers, the analysis of them. You can also do the analysis of heat exchangers, by the way. But we have a ratio over there, H5 minus H2 over H4 minus H2. Obviously, if you think back to your normal analysis with your constant or variation, sorry, your actual or ideal cycle, we can find all of those values besides H5. And once we find H5, H5 minus H2, which will be the actual regeneration. So just focus on that one. So basically, that will be the amount of energy being supplied back into the system. Yeah, so we will compute all of those there. Okay, so I think I did touch on this briefly, but of course, using your cold study assumptions, you can always get this beautiful thermal efficiency model. Make sure you know this, and I'm saying it now. What I might ask is just a basic application of what do you expect if you increase the temperature, the ratio of T1 to T3. And obviously, if you look at that, if you increase the ratio, you get a decrease in thermal efficiency. Whereas you increase it, the ratio of T1 to T3, obviously this is T1 to T3 in this case is the air entering the compressor to the exit of the exit of the combustion chamber, and this will basically tell you where regeneration is basically most effective. And what they show there, they're saying that the regeneration is most effective at lower pressure ratios. So interesting enough, is it lower pressure ratios? Yeah, 0.2 compared to higher. So depending, so there's without regeneration, yeah, and then this is with regeneration, yeah. So it's more effective at lower pressure ratios and also depending on your ratio. So go over that. This might be a sub question, a bonus question, so to say. Just an understanding of what you think is going to happen. Don't unpack that too much. Okay, so what we're going to do now, so make sure you have your previous question solved with the actual. You're just going to, again, extend that question further now. So what we're going to do, we're going to install a regenerator. And what it says there, determine the thermal efficiency of the gas turbine described in example 3, which is the previous example, if a regenerator having an effectiveness of 80% is now installed. So now we're going to see the improvement based on that. Subsequently, we're going to do a problem where we use a constant specific heat analysis. And this is the kind of level which you expected to do. The highest point, obviously, you either get the hardest one or you can get the ones in between for gas turbines. And this is where we have your isentropic efficiency, your compressor efficiency, and you also have your regenerator installed and effectiveness on a specific value. Okay, so let's quickly just add this question. This won't take that long. But I recommend you look at the previous questions. I'll share the previous excuse me, the previous whiteboard. So we're just going to extend on that. All right. Okay. So I hope you guys can see it. So let's just looking at the analysis we've done. Is this what question was this? Variation of this is using, is it constant? Oh, this is the whole variation question, right? Oh yeah, then we've extended it by adding, yeah. So we've got 26.63%, right? So I'm gonna just move along this way. And obviously I'm just gonna copy that part of the question here. Where is it? Okay, so, oh man, how can you just place it so small? What's happening here? Okay. So I'm gonna just obviously have that down for you guys, and then obviously I'm gonna copy and paste that models for you. So I'll lock that there, and I'll find the model which you require. So what's essentially new is this component here. Okay, so let's see how we're gonna unpack this. Okay, so, and I'm gonna obviously paste my TS diagram for better explanations in case people are just lost on it. So just to have an idea of what's going on. I did explain this last week, and you can see that is why I prefer just introducing a topic in one session versus crossing, but obviously the interest of time. So what we're going to need to do now is I'll look at my effectiveness, right? And obviously here it's going to be, we're looking for H5. We're going to look at H2, H4, and minus H2. But of course here, be cognizant, obviously, from the previous example, we had isentropic efficiency, so these will be the actual values here. Okay, H2ae, and we'll be looking for H5a. So just be aware of that. So what I want you guys to do now is find H5, and H5 is essentially this point over here. But you'll see, we will look at the two individual. So I'm just going to make you aware here. So the previous Q in, right? So this is how much fuel we basically use. We need, obviously we have to supply a specific amount of fuel to get a Q in, and the Q in was 790,791. Okay, 790,791 kilojoules per kilogram. Okay, previous Q in without a generator, right? So you guys can't obviously see this, but in terms of how much fuel was used, but obviously, we can fuel is your, let me just think about it. Q in is your calorific value, and if you remember your HCV times your mass. So obviously you're not going to do this kind of thing, but if you're using a specific fuel, it's a function of the calorific value of fuel, which doesn't obviously change. So let's say it's 22 megajoules, for instance. Then your mass has to compensate. Obviously, it increase more fuel to get a specific amount of Q in. Now, obviously, Q in is a very important metric because Q in determines it's within your thermal efficiency, right? And if you increase Q in, what happens to efficiency? Who can tell me? Students? Okay, yes, no one is, it reduces. Yes, thank you, Mr. Neto. And obviously, that, so we increase Q in, reduce. In this case, what we're doing, we're actually decreasing Q in by supplying more heat from the regeneration. So I hope that is clear. So I'll say it again. If we increase Q in, our thermal efficiency will drop. So what we're actually doing by adding a regenerator, we are making Q in less. So when we reduce Q in, we're increasing the thermal efficiency, right? Okay, so the effectiveness of 80%. I want you guys to work out H5 for me now. So this is the variable in question. You've got the effectiveness. Effectiveness is just essentially the efficiency of the heat exchanger. And I can unpack that if you really want. I mean, I don't want to add it in because it's providing another set of analysis. Okay. So I'll give you guys around 2 minutes.
Sir. Mr. Scott.
Oh, sorry, yes. Yes, I'm here. I'm here.
What is the value of the E, effectiveness?
Effectiveness is 80%, 0.8.
Thank you.
Yeah. It's in your textbook. It's page, let me tell you, I'm on it now. It's page 515. Guys, I'm always following some textbook or note, so just ask me if you just want to know where it is, and you can always ask me. Not supposed to be. Okay, so I'll just populate this in the meantime. So that's 0. Oh, sorry about that. So 0.8, H5. What is my H2 value? H2A, obviously. 605 point something. I think it's 179. Can someone just shout out that H4 value for me? So let me see H4 here.
880.36.
880.36. Good morning, Annalisa.
Morning.
Yeah, 825.48 something. So let's just have a look. Let me just make sure it's correct. 825 point, yeah, it looks a bit different from ours, but it's fine. 825.4, let's call it 49, right? 825.49 kilojoules per kilogram. Okay, so we got that enthalpy value. this is just basically the heat exchanger. So we've got that actual value there. So like now, what I mentioned to you now, we have to find the Q regen actual, which is, it's basically just going to be Q regen is H5 minus H2, right? So this is the amount of energy we're saving. In fact, this is the amount of energy we're supplying back into the, obviously we're supplying this to the compressed air after the compressor. All right, so let's just get that value. That's H5 minus H2. Yeah, just hope I'm right here. Let me just quickly see. Yeah, that makes sense. So it's 219 point what? 5552. Yeah, okay, I'll go with it. Right. So this, if I ask you how much energy was basically the energy supply, the amount of energy supplied by the regenerator, it's going to be this amount. But now I'm just going to show you something quickly. So now before we compute our thermal efficiency, and this is the point of where we're going, right? We've got to find a new Q in, right? And one could use logic, but simply the new Q in is simply going to be it's going to be H3 minus H5 now, and I'll show you now. I'll show you now exactly where it comes from. So it's H3 minus H5. So where does it come from? So remember, if you look at the TS diagram, normally from point 3 to 2 was our total, or 2A, right? That was our total amount of, what is this? Total amount of heat supplied. But now, obviously, we've saved the amount, so we saved to 20, but the actual amount supplied now, it's just simply going to be H3 minus H5 now, right? So H3 was a big value, somewhere over here. It's 1395.97 minus your H5 value. You'll see something which will come out of it now. Let me just calculate this. So that this is a new Q in. Q in, you can call it regen. So it's 135.9597 minus 825.49, and you get an answer of 570.48 kilojoules per kilogram. Okay. So just in comparison to the previous value, students, I hope you're following me. There's 790.791, if you remember. Obviously, if you subtract 790.791 by 570, you'll get Q regen. Anyway, so you can see how much energy you've basically saved. So this is a very key important thing I might throw in, and I'll say how much energy was saved using the regenerator, and it'll just be H5 minus H2, right? So in essence, we burn less fuel now. So obviously from that, we can compute our new thermal efficiency. Your work net stays the same, so your Q in is 570.48. Obviously, your work net is going to be, you've worked it out before, I'm not sure the exact value, but it's 515.61 minus 30 something, 304.98. And this is a new thermal efficiency adding the regenerator. So what is my new thermal efficiency? Yeah, 37.8. Okay, that looks good. $37.8 now, man. 36.78. 36.78, sorry. So if we look at our previous efficiency, it was 26.63, and as you can see, we've got to increase about around 10% due to adding our regenerator. What we're going to do now, we're going to do a question in the cap. We're going to do a whole question again. And you guys can't say I didn't cover the whole thing with you. So at least you have an idea now. But we do constant specific heats quickly. Is there any questions? You can keep it open for 5 minutes. Guys, any questions? You can just ask now while we are here. Like a question like this, if you look at the previous test, I think I posted it. That's around 30 marks. Big question. It's a very big question. So guys, if you're happy with this, I can just get it like I can get around 3 to 5 thumbs up, and then we can just move on and just solve the next problem. So we know new concept introduced now. We're just going to be applying now.
Sir,
Yes, there we go.
can you please go through this TS diagram with its regeneration?
Okay. Yeah, I thought so. Okay, so tell me what you know by looking at it. Yeah. Talk to me.
No, not this one. One like the model one. Okay, I guess this is the same.
Yeah, it's the same. Yeah. Yeah.
Yeah.
Do you mean do you want a normal one?
Yeah, like the standard one.
Yeah. Okay, the one like the ideal one, basically, right?
Yeah.
Yeah, that's fine. We'll start unpacking now. Like we have 5 minutes for it, so it's fine. It's good that you're asking. Is there anything confusing you, by the way, as you're just talking through it now?
Nothing really confusing. I'd just like you if you can just clarify what is actually happening.
Okay, no, it's fine. Yeah, go with it. Here we go. Let me just move along. Obviously, I said I'll mention this to you again. So this is a TS. I'm gonna just point my PV as well. Right? That's what's important as well. So I'll explain to you exactly what's. So remember what I mentioned to you. I'm gonna go holistic again, but with your PV diagram, normally what we tend to find, obviously, your pressure and volume, and you know this kind of thing. And over here, like I said, we normally use this for first law analysis, right? TS diagram we normally use for second law analysis because obviously we've got the entropy value. So what I'm saying is, obviously, because this diagram doesn't have temperature, we can just use this one as well. Okay, anyway. So I don't know what's your exact question, but obviously they're all linked, right? So if you look at point from 1 to 2, that's an isentropic compression. Therefore, this will be a straight line. That's obviously constant. 2 to 3 is a combustion. That's not obviously isentropic, but that happens to constant pressure. That's a straight line there, and essentially that line goes like that. Again, we have another isentropic expansion and a straight line over there. And 4 to 1 is basically your constant pressure heat addition. You have a line like that. So between points 2 and 3, that's where we add our heat in. Between point 4 and 1, that's where we reject our heat in. What if you guys have a bit more experience, and what it's telling you, and obviously I know a bit about it, is that when you normally have your external combustion will happen in constant pressure. Like so, for external combustion engine, this is the kind of model you want to adopt. But it's not, obviously, we're not getting to that kind of thing. So I don't know if there's any other questions with that. Did I miss anything?
When we have points 5 and 6.
Okay, 5 and 6 now. So now you want the regeneration counterpart, right? Okay. Yeah. So the next step, right, basically from this is now it's introducing isentropic values across the turbine and across the turbine and compressor. You actually do this with any device which is essentially turbine and compressor in anything, especially doing a turbine, and there's nothing obviously isentropic it's isentropic process, obviously having some efficiency. So what essentially happens, you shift your point 2 to 2A, which is over there, and your point 4 to 4A. So the compressor does a lot more work, basically, and the turbine does less work. essentially, right? So obviously with pressure drops, friction, and all that kind of things. That's the next step, right? You got that now. Are you happy with that one?
Yeah.
Okay, so next is the concept of regeneration, right? So I think I should have copied the one I explained to you last time. Is so all you must really understand about regeneration is that we're using our exhaust heat. It's like imagine using the exhaust heat, not the fumes of your car, the heat to maybe heat up the car itself. So what I explained last time, obviously you wanted the one of 0.6, so you should really worry about the 0.6 thing, and that's why I had the previous one up here. But the concept is just simple, is that we now basically redirect some of the exit heat into, so if you look at 0.4 to 6, right, we're taking some of that heat and we're basically supplying it back into 2 and 3. You get that part of it, right? So initially we had 2 to 3 Q in, and now we're just applying 4 to 6 into there. I'll tell you what 4 to 6 and 6 to 1 is. Does it make sense so far?
Okay, yeah.
Yeah, but you see, what I mean by 6 is that initially from 1 to 4, right? We had 1 to 4, but obviously now, if you want to find out the heat without regeneration, basically you have to subtract 1 to 4, and then from 6 to 4. But I don't ask that kind of questions. I'm more concerned with how much heat was added. So we're just adding extra energy in, before the combustion chamber. Therefore, we have to burn less fuel. Hence our Q in drops now.
Okay, it makes sense.
I don't know if that's, yeah, that's basically all. There's nothing more than that. Yeah. It gets
Okay.
more interesting, like you said, when you improve the system by incorporating intercooling and reheating after the turbine. Like that's where it gets, it's not difficult, but it just gets more fun. Okay. So I just want to make you aware. So this equation for constant specific heat analysis. Remember, when you're doing your constant specific heat analysis, especially in this case, all you have to do is essentially replace your enthalpy with temperature values. And obviously, it's easy in this case because it's constant pressure. So we're going to do the next one, which is a constant pressure analysis. And obviously, your book has a lot of those examples, hence me doing it. So expect both, but I'll obviously delineate the what's required for the test as best as I can, obviously without. So that's the concept, guys, and all we're going to do now, I'm going to give you guys some exercise to practice. So for you, this is from a tutorial from a colleague. There's a solution, so we're going to work through it and I'll post the solution. But I want us to treat this as an exercise, obviously in preparation for your test and exam as well. Right? Okay. So like I'm saying, this is the hardest you can get in terms of what you expected to know. Right? This is a concept you have to apply. It can get maybe a bit more fun, where they might give you the work output and you have to kind of work backwards, but it doesn't really happen a lot. But once you do more questions, you actually have we'll see. Okay, so this is the question. So Brayton cycle, the regeneration, that's how you know you're dealing with that. We're using air as a working fluid and as a pressure ratio of 7. The minimum maximum temperature cycle 310 and 1150 Kelvin. Assuming isotopic efficiency of 85, a compressor efficiency of the turbine 82%, and effectiveness of 65% for the regenerator. That's for heat exchanger. Determine the air temperature of the turbine, the net work output, and the thermal efficiency. So what we're going to do, we're going to use constant specific heat analysis, right? So if you remember that first question we did, is essentially the same kind of thing. Okay. So what I'll do, I'll give you guys around 5 minutes just to get a few temperatures. We don't need to find, obviously, all we need to find is T2 actual and T4 actual. So obviously, once we have those, it's going to be easy. So I'll give you some time to obviously practice so that you can solve it, and then I will obviously come and solve the problem at the end. So this is the benchmark, so you shouldn't worry too much. But I'll obviously at the end of the lecture, I will show you what you guys need to kind of go over, which is essentially the lectures, but different variations, you know. Yeah, okay. So I'm just going to go back to my whiteboard now, and let's see if you can have a go at it now. So treat this as practice, or a small tutorial, and yeah, let's see if you're able to do it. So we looking for the temperature at the exit of the turbine. So if I'm going to get my I can use my TS diagram. If it's fine with you guys, I'll just use my TS diagram. At the exit of the turbine will be what's it called now again? Where's the other one I had now? Let me just go find it quickly. Okay. So obviously the reason why I'm doing this is so that, you know, I when I can obviously show you exactly what the benchmark is. So we're doing our full question so you have a full understanding, I guess. So that's how your TS diagram looks with your actual, right? And your Q in, Q save, blah, 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 blah. Okay. Obviously ignore the temperatures over here. They're not applicable here. So in this case, we have 310 and we have 1150 Kelvin. Okay. So let's get our air temperature at the exit of the turbine. Obviously, at the exit of the turbine, that's going to be 4A, right? So I'm going to give you guys around 5 minutes, then I'll step in. If there's any other question you want to ask in between, you're free to ask. All right, are we winning? What's my T2 actual and my T4 actual? Who's got it? All right, let's see. And Elisa, what do you get with Doyle? Tumelang, how? You guys getting it? Okay, so yes.
No, I was just gonna say, so no, the brain is not working so well today.
No, man. Doyle. Stop
I know,
giving
I know. Not good.
No, it's fine. So this is T1, right? You all know that. So for constant specific heat analysis, which I said we must do, we know that T1 over T2 will be equal to P1. Is it P1? It's P2 over P1, sorry, to the power gamma minus 1 over gamma, right? So obviously T2 is just going to be T1 times a pressure ratio of 7, gamma minus 1 over gamma. Oh, T1 was given to us, obviously, and that's going to be at 310 Kelvin. So I can get T2, right? Once you find T2, if you remember your isentropic efficiency formula, right? We had, oh man, why did you just decide to do that now? What's going on? I'll just quickly check. Just give me a moment. Alright, guys, I'll say I'm back. Okay, back over here. So your isentropic, what do we call this? Efficiency to the compressor. T2. What is the formula for this again? You guys remember? Slides. Compressor does more work. Guys, are you still there? So H2S, sorry, not H2S, T2S minus T1 over T2A minus T1. I hope this is right. Let me just make sure. T2A minus T1. No, I think it's yeah, it is T2S minus T1 because your actual should be at the bottom. Let me just quickly sort this out. Oh, no, let me just do it like this, sorry. So H2A minus T1. I'm gonna flip this. Yeah, so this is T2A. And we have T2A minus 1. That equals T2S minus T1 over that, and then you're just going to have T2A equals T1 plus T2 minus T1 over that. Students, normally when you guys are quiet, you guys are not understanding what I'm doing. Is there any questions on what I'm trying to achieve here? Please engage. Are you guys just tired from the term? Just keep pushing.
Yeah.
Mr. Doyle, yes.
What? I'm a bit behind on my thermo studies. So when you say T2S and T2, when you say T2S and T2A, what do you mean by that?
Mr. Doyle, you're asking a bad question there. Remember,
I know that. So.
we have the ideal. It's fine. We have the ideal cycle. Then we have the actual one. We include isentropic efficiencies for the compressor and the turbine, and that's what I'm doing over here. That's what I mean. So the ideal is the S, and the TA is the actual value.
Yeah, okay, sure. I understand that, but we found T2S by doing the normal gas laws and stuff, right?
Yes.
And now we're going to find T2. We're going to find T2A with when we incorporate the efficiencies. Right? Okay.
Yeah, that's it. Yeah. Okay. And thank you for the question, guys. Please, man, we the tutorial kind of set up, so let's engage. You know, I'm past the lecture part now, so and I'm preparing you so that you don't have problems.
So,
probably I was more. Yeah, can I get my values? Just Siboya.
oh, I want this example. I didn't see where, like, what it's example number what, and maybe where did you get it? Did you get it from a book or something? I want to reference it when I'm writing it down so that when I'm going for revision, I can know where to get.
Okay, so before we get there, can I just have the answers? And I'll tell you now. Do you think you guys want to call it a day and you work on your own? We can do that.
So T2S was equal to 581. 540,528 for T2S.
Yes, 540. 40. Yeah.
Yes.
Correct. Yeah.
528.
528. Yeah. I'm gonna talk to you guys something interesting now. Anyway, you're gonna see what I'm talking about. And then obviously, have you computed 528? Yeah, Mrs. Boya, I'm now with you. Yeah, I'll show you now. Obviously, we're working on the 8th edition here. I'm assuming on the same thing. First question is question. Where is it? It's question 9107. That's what it is. Page 544. Yeah, and I think they've used variation on specific heats, but yeah, 5. There we go. Yeah, it's not so tricky for me. Okay, we're moving now, right? So what's next? I'm just obviously moving just through the actual question. I need to write a bit neater here. So T3 is given to us, right? And that's going to be 1150K. And if you find T4, that's going to be T4. Obviously, T4 is going to be a lot less, so it's going to be T3 minus your pressure ratio over gamma minus 1 over gamma. That's going to be T4. Okay. And T4, obviously, this is T4S, sorry. We still need to find T4A. So let's get that. Like I said, I will post that solution for this question. It's a whole tutorial back thing with questions and answers. So. Okay, I guess so. Let me work that out. So it's 1150 divided by 7 to the power 0.4 over 1.4, and beautiful Mr. Bell 659.54. Right, so obviously we have the isentropic value. Now to find the actual value, that's going to be 82% for the turbine, right? So if you remember that, obviously I hate writing this formula over because I normally just remember the what do you call it, T3 minus T4A over T3 minus T4S. To make that very distinct here, A and S. That's your turbine, right? Okay, so the efficiency was given as 82%, for efficiency of 82%. So let's get a T4A. Right, so T4A is just basically T3 turbine T3 minus T4S. So I will remember this. I know it's quite simple to use. Yeah, 747.9. That's good enough. And that's the first question, 747.9 Kelvin. And yeah, that's going to be the air temperature at the exit of the turbine. So obviously, because now we have a regenerator, they've requested us to work out our work net. And as far as I know, my work net stays the same, right? So I'm going to call this guy A. And I'm going to call this guy B. And work net is simply your turbine work minus your compressor work, right? This is the work coming into the system. And your turbine work is CP T3 minus T4A minus CP T, what's this guy called, T2A minus T1. So we're going to get the value of each one, obviously. So we are dealing with air, what is stated, It wasn't actually stated. Oh, it does say air. So, this is what I actually wanted to say to you guys. Index, where is this now? In a typical, in a question, what I'll just do, now, why am I going so far? Yeah, there we go. I can just go table A2, and I can tell Mr. Doyle, we have a prototype gas turbine engine. What we're going to do, instead of using air, we're going to use, which gas do you want to use here? We're going to use nitrogen. Well, that's exactly the same, so I probably won't give you nitrogen. Actually, I can give you nitrogen, because when you work at your heats, it'll be different. Octane, yeah, octane. Ha. So, do you guys get what I'm talking about here with constant specific heats analysis? Do you understand what I can ask you? Is it all clear to students? The variation, it's easy, we just have to use table A17. So if I feel a bit experimental, but kinky, I will decide, okay, hey, let me just see. Let me use a nice gas, you know, something. Let's use propane. Let's see how I will think. And obviously, what you must always know that if your gamma decreases, your thermal efficiency will decrease. So there are things like that you need to know. Okay. Nevertheless, our CP value here is 1005. T3, we've worked. Our T3 actual, obviously, is all, or the T3 is already given here. It's all actual values here. 4A was now 747.9 minus CP 1005. T2A, that's going to be 581.2 minus 1. Is it 300 Kelvin? Yeah, 310, sorry. So it's 300 Kelvin. All right, so let's just get those values. I'm just going to find out each one, and you guys can give me the final result there. 404.1105 kilojoules per kilogram. I'm not going to include the kilogram part. Obviously, we know it's going to be kilojoules per kilogram. Otherwise, it's going to take up space there. 5812 minus 310. Okay, so let's get my work net. This answer will be kilojoules per kilogram. That's my work net. Then we have to work on our thermal efficiency, which is going to be fun. Are you guys following? Yep, that's correct. $131.55. Anything close to that is acceptable. Okay. So I hope there's no questions till now, because now we have to find a Q in now. Because now we have to find so Q in, right? So remember, when we store a regenerator, our Q in has now become H3 minus H5, right? You'll see how much was saved in everything now. Obviously, we need to find H5, and if you remember, our effectiveness is equal to T5 in this case, minus T2A, divided by T4A, minus T2A. You get T5, oh sorry, this is now, so it's CP T3 minus T5. Or T5A, yeah, that's basically what it is. T5 or T5A, whatever it is. Once you have Q in, you find out your efficiency with a, you'll be marked incorrectly if you had to use H2 minus H3, because the question, you have a regenerator added. Okay, so students, are there any questions? Please ask. Let's compute Q in first. Oh, we have to first find our T5 now, right? So if our effectiveness given, it's always normally given. It's 65% efficient. Not an only effective heat exchanger. We're looking for T5. T2A was 581.2 Kelvin. T4A was 747.8 minus 581.2. And Elisa, can you please just get me that T5? Or I'll just call it T5. I don't say T5A. Yes, confused. Okay, let me see. Yep, I agree with that. 689.49. Okay, and obviously our new Q in is going to be 1005. T3 was 1150 minus 689.49, and you should get a value of 462.8. Ah. So my Q in was 462,8. Yeah, my laptop keeps, I don't know, I think it's something to do with the network. I honestly don't know. Yeah, and my thermal efficiency is just going to be, what is this called now again? What's my work net? 131.55 over 462.8. Yeah, 28.43. Yes. My check. What's my coal standard formula, guys? You remember it? My coal standard formula should work. Oh, I can't use it. Oh, I have a coal standard formula here, yeah. For my thermal efficiency, let me have a look. What's it? It's T1 minus T1 over T3. 1 minus T1 over T3 times gamma. I think that's this over here. Pressure ratio to the power gamma minus 1. So let's just quickly confirm if we get the same answer. 1 minus the maximum temperature is 310. Below it's what was it, 1150, and pressure ratio was 7, and this was 0.4 over 1.4. Just check this answer. And always remember the coal standard air assumptions, you can always check. I'm saying the same stuff over and over. And I get an answer of, that's strange, gamma minus 1 over gamma.
Your T1 is 310. I think you put 810. Or not?
No, I put 3, man. Let me just make sure my form is right here. I think it's my bond mass or something like that. Yeah, something suspicious. My pressure ratio was 7, right? Yeah, no, something's not looking right here. K minus 1, yeah. Not sure exactly. T1 minus T3. Yeah, it should have worked out. Something doesn't make sense. Oh, this is for an ideal cycle, sorry. Yeah. So this is for an ideal cycle. So it's kind of useless. It's ideal cycle, so we can't use this. Because we have actual values there. Sorry. Yeah. It's for an ideal cycle. It's being negligent. Okay. So are there any questions? Nearly at the end, guys. I've got one more problem to do. If you guys are comfortable, we can always we can call it. We can stop the lecture, and I can just give my final thing. Do you think you guys can do this? Students, let's talk. This is the next problem. Let me see who's here. Who's all quiet here? Mr. Kiefer, you're quiet. Mr. Silver.
Yeah, so
yes.
That previous question wasn't so bad.
Yeah, it's not. None of the stuff is bad. I mean, yeah, and this is now just with variation now. It's the same values, but with variation. So you guys can do it on your own. I can do it. This is also in your textbook. This is also 9107. Do you guys have any other problems? Can we discuss it now? Keep for yourself personally.
In life or with thermals?
No, with thermals, man. or maybe even the subject in general while we are here.
No, not really. I'm just struggling with electrical because that's a different subject.
Okay, that's good. I want you struggling somewhere. It's tight. Don't worry. I don't know, Ms. Jack or she wants to say something, or Mr. Siyama. So guys, can we do this one? Are you guys keen to do this one? Basically using table A17.
Yeah. Yeah, sure, let's do it.
Yeah, here we go. Thank you. Guys, you must always be fired up, man. That's the key, you know. Being really there, it's a lot. Yeah, you know, I actually want to have like a survey, but I'm just gonna ask the people who are here currently, you know, like what you find overwhelming about S4. And you can state obvious things. I just want to check something like either my subjects or you know, it's too much work. Do you guys find too much work? Is the work pitch at an easy level or the challenging enough?
Personally, so I would say I don't think the work is like too very excessive, but I find the
Yeah.
content itself to be quite challenging. That's just my
Okay,
opinion.
thank you. Yeah, no, it's fine. I think it's too much work. Yeah, there Sheila says. Yeah. Like the reason why I'm asking this question, in my time, I never did. No one would ever do Mom3 and Electro 3 together. Like certain subjects you never just do together in one semester. People normally do, if they're going to do Mom3 and Electro 3, they'll have only done the two subjects alone. Thermos and strength 3 was always fine. That's okay. Thermos, yeah, strength thermos, like you could have managed, but we have strength 3 in another semester. But yeah, but I'm just letting you know, like in terms of, and also obviously we never did like 9 modules and had 9 exams, so max 6. So yeah, it's that kind of thing, man. So I'm just checking. Anyway, okay, right. So let's move on the last problem for the day, and we're using variation of specific needs, guys. Right, table A17. After this, you probably will not see this table. You might see it in the refrigeration variation of specific heats. And guys, make sure you can get marks for this stuff. I mean, so much marks to get. The pace is also on the high side. Ah, there we go. The pace. Yes. Thank you for mentioning that. Yeah, you know, I think. Okay, Silas, can you say something and then Mr. Kiefer? I'll get on that. Yes.
I just wanted to clear with something. Does the question always state that you are going to have a variation? Yes. Okay.
Yes. Yeah. Always. It'll be very clear. Too much work, always under pressure. Yeah. See. No, they're not pitching it at the right level. I think I'm not going too far in and stuff like that. I also, with certain sections, I also want to produce a certain amount of depth and not just keep it like, what one can also do is have like a lot of modules, a lot of different sections, which is boring because then your learning is not proper, it's not done proper. But if you go into in depth with a specific section, your understanding improves a bit, in my honest opinion. Nevertheless, let's unpack this guy. So they require the same stuff, and I'll mention anything extra which is important, which you should know, right? So it's the same parameters basically. So obviously you have to use table 17. So checking at the table, you take T1, 310, and you can have a look. So you need H1 and PR1, right? You just get those. And then I'll leave you on the next one. Your pressure ratio is PR2 over PR1. And obviously you can get PR2 based on this. And then from PR2, you can get H2S. We don't actually need temperature in this case. So let's get H1 and PR1. I have so much table here. I can't. I'm not pulling this script. There we go. Did I put up the question papers for what is this called again? For what is this called again? For thermals. Yep, H1. What? Mr. Neto, you're getting O. I was going to say now. 310.24. Yes. Don't forget the unit. Obviously, the radial pressure is. And from PR2, using a pressure ratio, it's just going to be 1.5546 for 155 PR2. It's just 7 times. And you should get 10.88. Let's see, just do the enthalpy value here. Okay, who's making a noise? Mr. Doyle. Let's mute him there. Okay, so let's get H to S. Obviously, you're going to have to interpolate, I think, there. After H to S, we can find the actual, what is this? Which is going to be H2S plus H2S minus H that, and then, okay. So I hope the concept is there. I've got my table next to me, so I'm quite. Now 541.26, 256, that looks good, yeah, 256. And in fact, now you're practicing for your exam, so I'm just letting you know, when we solve these problems, we're actually practicing. But obviously for you guys, it's it must be part of your memory because you sit down on exam and you have to manage your time. So that's the hard part here. Your isotopic efficiency was a compressor 75%. In this case it's 75%. I think the previous one I added different, so I apologize for saying it's nearly the same. Minus 310.24. Okay. H62. No, what am I getting? It's wrong. Sorry, it's 618. See, Mr. Minus is back on his groove now. Yeah, 0.26. That's correct. Yeah. All right. I'm gonna put you off with T3. Right. T3 off the table. 1. What was it? 1. Is it 50, right? So obviously, to get that values on the table, one is to divide by 2 now. So in this case, it's going to be 120. Sorry, not 120. It's going to be 1184. I'm assuming you guys do know that. If you have, if you're looking for a value between 2 values, you just have to find the average of them. So T3 was 1150. You're obviously going to need H3 here, and H3 we're going to need, and PR3, H3 was 119. Am I right here? Let me just make sure before I. It's 1150, so it's 1207. Yeah, 1207. I made a mistake here. I put in the wrong value. 1023030. 1230.92. So it's 1219.25. 1219.245, sorry. Yeah, kilojoules per kilogram. And for PR3, it's just basically between the 2 values there, which is 207 and 193, I think. 200.15, yeah. I don't know if I'm going too fast for you guys. So what I'll do now, You guys keeping up? I can give you 5 minutes to catch up, and then just so long so we all get to our properties, and then we can start working out. So I'll give you a few minutes to get to the temperatures, get the actual temperatures and the large entropy, and then we can look at the last part basically. Are you guys all there still? Are you guys fine? Who's not following? Please ask if you're not following. Okay, so I'll give you guys a few minutes to get to the temperatures. So obviously okay, let me just sort this out for you guys. So obviously, where you want to be now, you need to find PR4, then that's PR3. I'm sorry, yeah, there's PR3 divided by 7. Obviously, your pressure has to drop, and you should get a value of 28,59. Right, so you're just taking this value here, 200.15, dividing by that, and obviously from this, you get your H4S. You have an efficiency, and an efficiency for turbine was 82%. Yeah. So I'll leave it like this. Okay. All right. So I'm assuming you guys got it. Your H4S value should have been, where is it now? 711.80 kilojoules per kilogram. And then to find your H4 actual, that's H4S minus that, your isentropic efficiency across your turbine, times H3 minus H4S. And that's 711.85 minus 0.82. H3 was 1219.45 minus what's H4S? 711.8. Okay, so I've given you all time to get to that part of this, which is 823.1365. Yeah. Okay. So once you've got this is the least you should be able to do. You should obviously find your okay. They ask for the temperature, the exit of the turbine. So this we have to find using my interpolation. So I look at my enthalpy values, where it's 803 kilojoules per kilogram, and that's between this is between 780 and 800. Between, and I'm assuming you guys got that temperature there, right? So yeah, that's because I requested that. 782.83. Yeah, that looks right. 782.83. I just want to see if I use my what is my T4 at the previous T4 T4 was 747. T4 constant was 747 Kelvin. So yeah, fairly close to each other. That's just in constant specific heat. Obviously, we're not dealing with that. Right. So now I wanna quickly, before we move on into finding the network output and the regenerator need. So what I normally do for the test, I'll say find before the installation of the regen, right? So let's conduct analysis before we actually put in the thermal efficiency, before we install the regenerator, right? So that's still going to be work net divided by Q in, and obviously we need to compute this two stuff here. Another thing we're not computing is the work back ratio, so be cognizant of it. It does come up. So our Q in before the regeneration is, can someone tell me, just give me the enthalpy values for each one here. So Q in before regeneration, what is it? So Doyle, Lisa, Ms. Jack, Mr. Seyama, Silas, before regeneration. What is it? Guys, Q in is H3 minus H2A, right? Our turbine work is H3 minus H4A minus H2A minus H1. That's a compressor work. Are we all happy with this?
So I didn't get that H2A value that you got.
H2A?
Yeah.
Why not? What did you plug in? Oh, I think I know why. I know why. It's because I put the wrong values here. This is H1. I just realized now. It can't be. I'm putting H2 there. It's H1. Sorry, man. You guys are not checking on me here. H1 was 310. That's why it's me. It's me. It can't be H2 there. Yeah. That's why. Sorry about that. 2.4. That's why I'm catching on crack. Oh, you found it here. So H2 plus H1 plus H2S minus H1 divided by that. Okay. So let's find it before installation. Let's see what we get. Obviously I'm not going to install. I'll have to have the work net so we can have it for the previous one as well. So where's my H3 again? It's 1219.245. Guys, I hope you're getting the concept here. H4A 1365 minus H2 that is 618.26 minus H1 was the 310. Divide this by H3 was 1219.245 minus H2A, and that was going to be 618.26. Okay, so what's my thermal efficiency before we install the regenerator? I'm going to work out my work net in the meantime so that we have it. Okay. No, why 60? I think yes. So work net is what's 108.0905. I hope you guys agree with me there. And my Q in is 1219.245 minus 618.26, 600.985. So is this cool? What's going on here? Yeah, it is definitely 600. Is my work net right? I'm getting very high work net here. It can't be greater than this. What am I doing wrong here? 1219.245 minus 803.1345. That's 416.11. And that's 618.26. Oh, I know what I did. It's in the calculator. 310.24. And that's 308.02. Students, are we all still there? $416.11 minus 308. What's the 308 point? 308 point. I don't know what it was. What is the name? Just get this right here. 618.26 minus 310.24. Yeah, 108. So my work net is 108.09. Oh, 108. Yeah, sorry. Yeah, it's correct. Yeah. So that answer 108.0905 over 600.985. You get around 17.9855 or 6%. That's before my regenerator. Are you guys okay with that? Is there any questions before I move on? You guys are awfully quiet, and when you're quiet, that means you're lost. Hello? Jason's got it. Anyone else? Thank you, Brent. Anyone else? Oh, so sir, when you are given both turbines, yes, that is correct. Yeah, Mr. Ziboy, I just saw your question now. If you're giving you efficiency at the actual cycle. Okay, thank you. So when you install the regeneration now, so installing regenerator, we know that our Q in is going to be H3 minus H5, and now we've got to calculate H5. So our formula for our H5 is this. I'm sure we've just been using it. Effectiveness of 0.65, you remember. So now we've got to calculate H5, and now you can see our new Q in. And if I want the Q regeneration, so how much heat was actually produced by the regenerator, the heat exchanger, that's going to be H2 minus, what was it, H2 minus H5, I think. Basically, how much energy was saved, right? So let's quickly get at H5. Someone got it already? 738. Let me confirm. Yep, 738.43. That's correct. 738.43 kilojoules per kilogram. And obviously now we can find our new Q in. What are we expecting? Obviously, it'll be less than the previous one. So let's just quickly get that, and then obviously we can compute our thermal efficiency over here. Let's see. Okay, guys. Yes. So yeah, the Q in was 480. 0.83. That's good. So that's now when we install the regenerator, right? So as you can see, it has dropped from 600, which you normally required, to only 480. Your work net, what we found was 108.0. Now, I think it's still inefficient gas turbine. That's for 80.83. And if you find this, you should get around 22.5%. Right? If I ask you how much energy the regenerator has, how much energy we saved, energy saved is essentially Q saved is equal to Q regen. Also, it's equal to Q in before minus Q in after. And it should be, it's just essentially H2 minus H5, or you can just say 600 minus 480, which is going to give out approximately around 280 kilojoules per kilogram. All right. So guys, that's basically the end for today. And I wish you all the best for the test. But before I conclude, I just want to go back to my slides here. And so just to state over here, like as Mr. Romano said, I'll just write it here, guys. Just give me a moment. Auto cycle. So it will be CP and constant and variation. Auto and diesel. Dual, you just keep it constant. For your Brayton cycle or Joule, which is obviously the gas turbine one, it will be constant and variation. Okay, this will be around 70 marks. Fortunately for you, 2 hours, 30 minutes. So you have more than enough time for everything. Obviously, watch all the lectures. I've mentioned a lot of things happening, so I hope you guys have enough. So I'll see you guys next time, the 20th of September. We'll start on refrigeration. Yes, Silas?
Say, is 2 hours enough for this big question like this one? Yo.
Yeah, it's enough. 2 hours, 30 minutes. If you've practiced auto and diesel, or auto, diesel, and dual, so you won't get you get 3 questions. So what I'm saying is, to be specific in this, for this assessment, you'll get the auto, but you either get a diesel or dual, because this is essentially the same thing. So it'll be 3 cycles. It won't be 4 cycles. It'll be 3 cycles. For instance, I might give you one regeneration. And remember, guys, I don't make everything equally difficult. So one question will be more easy than the other one. One will be more harder than the other one. You know, that kind of thing. I am cognizant of that. But like I said, the tests are easy. The finals, the one where it becomes a lot tricky. Because then you're dealing with this 3 plus a whole another 4 chapters, basically. Which is also fairly easy. So this is the best time to score marks. Oh, the next 2 chapters you can score marks. Yeah, but the finals are hard because there's a lot of content, man. Yeah. Guys, there's no any questions moving forward. Now we can adjourn, and all the best. I will be somewhat available during the next week, but what I'm essentially focusing on is preparing the tests I've got 3 tests to prepare, and I have to prepare the examinations. I'm not done with them yet, so I'm going to be extremely busy with that. Obviously, I've got a few personal academic stuff I also need to achieve, but I'll try to respond. Obviously, it's a bit more easy now since I don't have to lecture, and also for moms, I will be I have some work for moms to do, obviously, but things will be a bit easier since that I don't have to directly have a lecture, obviously, which takes the timing. Yeah, but anyway, guys, thank you very much, and see you when I see you for your first test. On campus, information will be shared accordingly. Thank you very much, but enjoy this weekend, right? Before we get back into it. Okay, guys, cheers then.